All right. Hey, what's up, AP Chemistry? Welcome to the very last chapter of the 2024 school year. And just like we did at the start of the year, I have a little like picture of a kid falling out of a raft. And there's been some rapids along the way as we wrap up. And the last one is, I mean, obviously, most of them have been for me, honestly. But you guys have gone through your own, set of challenging circumstances this school year. So, anyways, this is our very last one. We are going to wrap up buffers and titration curves this week. We'll start a review a little bit. Um, Basically, the course will just basically run out the next 3 weeks. That's all it is. I mean, there's no point in doing a bunch of stuff after the exam, right? Like, I could teach you stuff, but like, the point of the class is to get you ready for the AP exam. So, that's what we're going to do. Okay, so we still got this. Most of the year I've spent face to face. Most of you are doing okay. Remember, our three big numbers are 80%. That's your goal for a five. 65%. That's your goal for a four, approximately. And 45% is a goal for a three. So, but if you shoot for 45%, you sometimes hit lower than that. So I wouldn't shoot for 45%. I would at least shoot for the 65%. That way you at least pass the exam. And most schools take fours. Um, you know, it's hard to get a five, but you can do it. I believe in you guys. Okay, so today as we go, we're going to start buffers. And buffers are these really cool things, this like system that is actually it kind of utilizes something called the common ion effect. So I just want to kind of talk about this right here. So let me get my pen out. Okay. And we're going to go here. And I feel like we need like darker colors. That's going to be better. Oh, yeah, that's perfect. Okay. So, um, so a buffer, or before we get into that, I want to talk about like common ion effect. So if we have this right here, which this is a weak acid. So if I look at my equilibrium expression, it's Ka is equal to H plus C2H3O2 minus all over H C2H3O2. Okay? And that's your equilibrium expression. You will at least get 1 point for writing that out. It's somewhere on the AP test. So you just remember that it's products, right, over reactants, and never include water, and you should be good. That's nothing. That's a mistake. All right. Now, what the common ion effect does, and this is really all that buffers are, is it says if we introduce a common ion. Okay, so what is a common ion? So a common ion is something that's part of the equilibrium expression. Then it's going to make the equilibrium shift either to the right or to the left. So if I take NaC2H3O2 and I add it to this system, okay, as soon as I add it, so because sodium, anything with sodium in it is always an electrolyte because everything with sodium dissolves. So it's going to break up into C2H3O2 minus and also Na plus. And Na plus is just going to sit there and spectate, so it's not going to do anything. So if I add some common ion, what's going to happen is this equilibrium is going to shift. And it's going to shift to the left. All right. Now, if this is an acid, and it is an acid right here, okay, so this is an acid. This, by chance, is actually called its conjugate base. I don't know if you remember that, but that's its conjugate base. So a question they're going to ask you often is if you add a common ion, what's going to happen to the pH? Well, if it shifts to the left, you're going to make less H plus, so the pH is actually going to go up. So you'll see that in some of the Pearson stuff that we do, but just understanding that there's a relationship with common ions, and that's really all that buffers are. Is there's a common ion introduced. Okay, so let me go on to the next slide. All right, so here's a common ion effect problem. So in this one, what they're going to do is they're going to give you guys all right, they're going to be like, all right, here is your benzoic acid. Yeah, it's benzoic acid. And then here's the whole equilibrium system. And remember, it's always reactions with water. And my Ka is always like Ka equals products over reactant C6H. I'm going to have to change color. That's why it was a different color, because if I go over, okay, HCOO, whoa, I made it too big. Like, why would they do that to me? That's just crazy. Okay, so anyways, I'll put it over here. So Ka equals C6H5COO, right? And then H3O plus, and then that's all over C6H5COOH. Okay? So in this case, what they're going to say is they're going to give you the initial concentration. And when you don't know what to do, if it's an acid-base problem, it's probably a Ka, Kb problem, right? This is always going to be nothing, right? This is going to be 0, but this time what's going to happen is this is going to be, this guy is going to be 0.15. See how they tell you that there's a common ion involved in this? So then all you have to do is just plug in stuff. So we know this is going to be X, this is going to be plus X, and this is going to be plus X2. And then at equilibrium, this is going to be X, and this is going to be 0.15 plus X. And this is going to be 0.25 minus X. Okay? So then what you're going to do is you're just going to plug everything back into here. So I'll show you the expression here, and then I'm going to talk about pKa. Okay, so all right, so this would be X times 0.15. Now I want to mention something. Because these are all weak acids and this is going to be super small, you're always going to get rid of these X's here, at least those two. So instead of saying plus X, it's just going to be 0.15. And down here, it's going to be 0.25. And you're not going to say minus X because, again, that X is really small. And that's going to be equal to the Ka. Now, in this unit, instead of them giving you Kas, they're going to give you pKas, which is the negative log of the Ka. Now, why do they do that? Well, it has to do a lot with like pH and buffer properties and stuff, but it's just by convenience they do this. So Ka and pKa are basically the same thing. You have to do 10 to the negative pKa to get it into Ka form, just like pH. So you're going to do 10 to the negative 4.19, and voila, you get your awesome answer when you solve for X. And these are actually a little tiny bit easier because, um, you can actually you don't have to do as much work. There's no square root and all that kind of stuff. But there's always going to be, and usually it's in the FRQ, some buffer problems or some acid problems, and this is just an extension of the previous unit. It's not that bad. Everybody gets dramatic about it. Kids, they like drama, right? Okay, so this is done the same way. So I'll show you. I'll run this through one more time. If you get this, you can skip it. But HNO2 plus water. You always start with your formula, right? And then it's going to be NO2, and this should be nitrite. This is a mistake. NO2 minus plus H3O plus. Okay. And what you're going to have is you're going to have ice, and it's going to be 0.085. All right, this is going to be always, nope, don't put it in. This is going to be 0.1, and this is going to be 0. And then at equilibrium will be minus X. It's always minus X, plus X, and then plus X. And that equilibrium, that's what it stands for, right? It'll be 0.085 minus X, and you get better at writing, 0.1 plus X, and then this will just be X. Okay, so get rid of that plus X. All right, so then we plug it into our equilibrium expression, but what I can do is I can get rid of these guys right here. And the reason, again, is because they're super duper small. So it's going to be X, which is the products, right, times 0.1 over 0.085 is equal to, this time they give you the Ka, which would be 4.5 times 10 to the negative fourth. Okay, so then what you're going to do is you're going to solve for X, which if you know H3O plus, you actually know the pH. So then what you're going to do is once you find X, you're just going to do math. I'm not going to do it right now. It takes too long for me to punch it in. And you can punch it in and get the right answer. So do that. But this would be, X would be, the pH is actually the negative log of whatever answer you get because pH is negative log. All right? Are you smelling what I'm stepping in? Does this make sense? All right, let's keep going. So this brings us to buffers. So buffers are a specialized case of acid-base solutions that actually contain both. They both contain, they're made of either a weak acid and its conjugate base, or they're a weak base with its conjugate acid. Boy, I'm having problems writing. And what that means is that they actually have a mixture of both. Okay, so for example, here, this is vinegar, right? Vinegar is a weak acid. You could just take vinegar if you want to make a buffered solution. And then this would be acetate ion. Usually what happens is they usually find something that like spectates and combines it with. So like KC2H3O2, group one elements to just spectate the whole time. So it's not going to do anything. So anyways, so this is a weak acid and its conjugate base. And what happens is if you add an acid to this solution, the base part of it, this guy right here, will take it on. And if you added acid or a base to the solution, the acid part will take it on. So since it has both, and if you add one or the other, it'll just cause this reaction to shift right or left. It's all back to Le Chatelier. It's always back to Le Chatelier. But that's what you do. Okay. So let me show you guys some stuff with buffers. Okay. So concept question. These are always good. So we make a buffer by adding NaC2H3O2 to a solution of acetic acid. So I have my weak acid, HC2H3O2, and then I add this part to it. So that's the C2H3O2. And there's always somebody that spectates. Usually it's sodium, potassium. Okay, now what's interesting about this next one is this is a weak base. Okay, so ammonia is a weak base. So now I'm going to add its conjugate acid. So you have to think conjugate acid is something with NH4 plus. Now you can't just go in the back of the prep room and grab NH4 plus. There has to be something with it. So something that an anion that's commonly that's like spectates is NH4Cl. Okay, so we actually have that back there, and that would be that. This would be the Cl is just going to spectate, and it'd be NH3 and an NH4 plus. Okay, now what? Look at this question down here. Which of these can you actually make a buffer from? All right, well you can't make it from this one. That's a strong with a strong. And what happens is since the strong components, remember how their conjugates are negligible, they lack the ability to take on the other part. You know, this is a weak acid, so it can take on bases. This is a weak base, it can take on acids. So these guys, both of them are present. And this one, only an acid is present if you neutralize it one way, or only a base is present, depending on which one you have excess of. You can't have both. All right. Now, in this case, they're trying to trick you here. These are actually different things. This would work if it was NaNO2, but in this case, it's not. So, nope, it's not that. And then this one, this is again strong, strong. So it has to be a weak acid with a weak base. Let me talk about this one. So if you take HF, and this is kind of cool. If we add a little bit, and not all of it, but a little bit of OH minus, you are going to make F minus and water. And so you can partially titrate, which is what we're going to do at the end of this, and you can make a buffer that way. So there are two ways to make a buffer. You can just mix stuff, a weak acid with its conjugate base, or you can partially titrate a weak acid or a weak base, and you also make a buffer. So jot that down. Two ways to make it. You can either add stuff, like right away, or you can titrate it. And so at the end of the week, we'll do some titrations with it. Okay. So it was a trick question. Always is a trick question. All right. So what's an interesting thing is, and I was mentioning this, is how a buffer works is one of the components is going to take the other one off. And so you're going to kind of get used to writing the equations. But if I have a weak acid, weak acids are going to take on bases. So this is my weak acid. This is my base. And notice I'm going to always make water when you neutralize an acid, but I made more conjugate base. So what happened is I actually made another part of the equilibrium system. Remember, the equilibrium system contains a weak acid, I'm going to call it HA, and its conjugate base. And so these two, since they're all part of the same or common ion, where there's an ion common to that situation, then it's going to work together. Okay. And this guy, this is my conjugate base down there. And same thing. If I add acid, remember H3O plus is acid, I will get a weak acid and it's conjugate base. So these things, this is how you take on acids and bases. What's interesting about buffers is it's used in our blood. If our pH changes too much, we die. So our body is amazing, right? And um, it has a buffer system to it that prevents that from happening. All right, so this is just showing you, you know, if there's, and they'll ask you questions like, all right, what part will take on the H3O plus, or what part will take on, and just remember that there's always the acid, so the acid part and then the base part. And if I'm adding H3O plus, okay, then oh my gosh, if I add this is going to take on the H3O plus, and I'm going to make more of this, and so it's going to shift a little bit, but it doesn't shift like a lot. I mean, it shifts a lot, but not as much as you think. And so the pH kind of stays the same. Buffered solutions, basically pH, it doesn't change much. And that's what makes them cool, is the buffer prevents it. All right, so these are done the same way as common ion problems. They're just ice problems. So if I have benzoic acid, which I do, and I have 0.12 m, again, this is not there. And then I have sodium benzoate. Sometimes like benzoate is like C6H, a big thing, but they'll shorten it up like BZ. There's no element BZ, it's just shorter. Because remember, every acid is always HA, and then the conjugate base is always A minus. So they're doing it that way. And then this is 0. And this is going to be minus X. This is going to be plus X. Plus X. Wish I could write better. 0.1. This should be minus X, not. This is 0.12 minus X, and this would be 0.2 plus X. Again, this is a little bit different than before, and this would be X. And so at equilibrium, I'm just going to write it as here, Ka equals 0.2, and we're going to drop the X here, okay? Because compared to 0.2, the X is really small. We're not going to drop this X because that's the point of it. We're trying to find pH. pH is directly related to H+, and then this would be 0.12. And then you just plug and chug and solve for X, and then take the negative log of X to find the pH. And I'll post another video from someone that's better at writing, and you can check that out as well. But essentially what you're trying to do is you're trying to figure out what is the pH, or what is the H3O plus of this solution. Okay, let's do this. Let's keep going. All right, now there happens to be an easier way, and this is the Henderson-Hasselhoff equation, or Hasselbalch equation. I always call it Hasselhoff. So pH is equal to the pKa, okay, so plus the log of the base over the acid. Okay, so if I'm doing this, and this is actually just a shortcut, it's super good. So you find the negative log of the Ka, whatever it may be. So sometimes they'll give you the Ka, or sometimes they'll give you the pKa. So they give you that, plus the log of the base. Let me go back. Let's just double check this. What was the base and what was the acid in last thing? Oops. Okay, see how the base was 0.2 and 0.12. Okay, so 0.2 over. So this one would be, it'd be pH equals the pKa, again, the negative log of the Ka, plus the log of the base, which was 0.2 over 0.12. It's kind of like it takes the ice problem and kind of solves it ahead of time for you. And so it's faster, it's easier. So you can use the Henderson-Hasselhoff. In fact, it's probably preferred. I always say Hasselhoff. It's Hasselbalch, but Hasselhoff is like David Hasselhoff from the SpongeBob movie. He makes me laugh. Okay, so now they're going to ask a ton of questions about it. And first off, they're going to shoot you things like this, like what is the pH of a buffered solution consisting of 0.15 moles of NH3 and then 0.25 moles of NH4Cl. And this is my, right here, this is my weak base and this is my weak acid. So we know the pH of this is going to be greater than 7. So, but we'll do this real quick. We'll make sure. So pH equals the negative, or equals the pKa plus the log of the base over the acid. Now, since they did this to you and this is a base, this is actually exactly opposite. Okay. So what you're going to have to first do is find the pKb and subtract from 14. So if the uh, pKb is, this would be the negative log of 1.8. I'm going to impress you. So the pKb would be 4.74. Check my work. I did that mentally. Took the negative log of that number right here. And then, so the pKa would be 14 minus that. So that would be what? 9.26. So 9.26 plus the log of the base. So which is my base? So it would be 0.15 over 0.25. Since they're in the same solution, you can just go straight to moles. And so you would do 9. It should be 9.26, not 62. Maybe I'm dyslexic a little bit today. And then 0.15 over 0.25, and that'll give you your pH. That is how you do it. Now, another way to look at this is we know the pH is going to be, okay, since I have, so the pH and if the base and acid are the same, then it's just going to be log of 1, which is 0. So the pH would actually be, of the perfect buffer, would be the pKa. So if I'm adding more, in this case, I have more acid. So the pH should go, it should be less than 9.26. So check it, calculate it out, make sure it makes sense. Okay. Now, buffer composition. So you can play around with this. So we're going to use the preferred method is the Henderson-Hasselhoff, but you can figure it out either way. So again, punch these in your calculator, solve along with me as you go. So we would know the pH, 4.64. And so it's pH equals the pKa, that's the negative log of the Ka, plus the log of the base over the acid. Use this exclusively. Okay, so pH is equal to 4.64. And then the pK, you have to look it up, and it happens to be 4.74 plus the log of the base. Okay, so the base is going to be X over the acid. See how acetate is a base? So then you just do math, right? So this is going to be negative 0.1 is equal to the log of X over 0.13. And then you just have to get rid of the log by taking the antilog of both sides and then just solving for X and just mathing it out. So take a second and do that math part, punch it in, write your answer down. I did the hard part for you. I plugged it all in the formula. Now you just got to plug and chug. Okay, and then take a look at down here. Same thing. So buffer has a pH of 4.27. Again, you plug it into the Henderson-Hasselbalch equation. And then this is the acid part. And then you just have to look up what is the Ka or pKa of cyanic acid. Okay, so let's look that up. So I'm going to put my pen down for a second. Sorry. So you can either look them up. There's Appendix D in your back. So pKa of cyanic acid. Let's see what that is. 3.46. Okay. So you would do 3.46 and then do your thing until you get it just right. Okay. It's the same thing. Okay. So let me trash that. Let me keep moving on. All right. Now I want to mention the last part about buffer capacity. So buffer capacity is how good the buffer is at taking on acid and bases. So what happens is your acid or base components of it, there's only so many moles that they can take acid, on acid or on base. And so the best buffer capacity, the best buffers are going to have lots of acid and lots of base. And what I mean by that is they'll always have lots of the weak acid and lots of the conjugate base. The problem is, okay, and I want to mention this. So if you have a buffer of 0.01, let's just do HF because it's easy to write, and then 0.01 NaF, okay? This is my weak base. This is my weak acid. Like, it's going to be able to take on acid or base, but its buffer capacity is less than something that has 0.1 and zero point 0.1. And the reason is there's more. Okay, so this can actually take more moles than this guy. So sometimes a buffer, if you don't have very many, it'll just like not withhold. It won't change. It'll change drastically once you overcome either the acid or base component. So in general, here's the rule. So in general, it's plus or minus 1 of the pKa. And what I mean by that is, like, let's say we're talking HF. HF has a pKa around like 3.7. So my buffer is going to work best because I'll have the proper ratio of each if it's somewhere in the range of 2.7 to 4.7. That means I don't have too much of one or too much of the other, because when we're talking about it, we're talking about pH equals the pKa plus the log of the base over the acid. This part, this guy right here, has to fall within plus or minus 1 of the pKa, or it's not going to work. So if I want to make a buffer that has a pH of 7, I can't use acetic acid that has a pKa of 4.74, because it'll exceed part of it. Like, you're going to add so much base to this to get the pH up to 7 that it will have so few acid that it'll just not work. So that's what they're talking about. Okay. All right. I think that might be it. Let me see. Yeah, that's it. All right, I'm gonna show you some other examples. I know this is hard, but do your best, right? Like, you don't have to be perfect. Remember our numbers that we talked about, and let's do this. Let's go. Let's finish up.